I can start?
I can start.
Good afternoon, friends. So I understand that this is the second series of the talk for the fisheries oceanography for the professionals, right? So I will be talking about the ocean biogeochemistry, some fundamentals, and since it is a basic course, I will not go into the detail, but I will try to give you a flavor of what ocean biogeochemistry is and how nutrients play a major role, or what is the nutrient process in the ocean biogeochemistry. I hope you all can see my slide. So as I said, I will talk on the fundamentals of ocean biogeochemistry, mainly nutrients, productivity and nutrient cycling. If there is any doubt, you can reach me on satyap@incois.gov.in. To start with, I would like your attention on this figure, which is the annual climatology of the chlorophyll in the ocean. So in this talk, we will try to understand why we need to look at the chlorophyll and what are the factors that govern this chlorophyll distribution in the sea. But before going into the chlorophyll, let us have a look at this slide, which I always keep as my first slide, to emphasize that why we should have some background or some basics about the ocean biogeochemistry, how ocean biogeochemistry plays a role. So if you look at this slide very carefully, there are two plots. One is in the red color, which shows the temperature, and the another one is in the blue color, which shows the carbon dioxide concentration in the atmosphere. And this slide gives a synopsis of, say, the past 450,000 years. In this slide, you see that there is a strong relationship between the CO2 and the temperature. Wherever this temperature is high, the CO2 is high, or the CO2 is high, the temperature is high, and when the CO2 is low, the temperature is low. But what is interesting in this plot is no matter how far we go into the history of the earth, which is shown on the y-axis, the concentration of the CO2 has never gone beyond, say, 260 to 80 ppm. So what has changed in this recent past? The recent past, when I say recent, it means, say, around 100-150 years, the concentration of carbon dioxide in the atmosphere has increased dramatically, and this is partly due to the industrial revolution and the fossil fuel burning. So the concentration of carbon dioxide in last, say, 150-160 years has increased beyond what Earth has ever seen. We saw in the last slide that the concentration of carbon dioxide has never gone beyond 260 to 80 ppm, but here we say that it has a bit old data, but now it has almost crossed 410. What it means for the atmosphere is that the increase in the carbon dioxide, which is a greenhouse gas, has led to the increase in the atmospheric temperature, or the what we say in the scientific term is the global warming. But the rate of increase is high in the recent past compared to the earlier, as we move more into the industrial era and more fossil fuel is being burnt. But if you estimate, or if one tries to estimate the amount of fossil fuel that we have burned in last 50 years and the consequent rise in the atmospheric carbon dioxide, it's not one-to-one. What I mean to say is the amount of carbon dioxide released because of fossil fuel burning has not entirely gone into the atmosphere. A part of it has been removed by the ocean and the land. So if you look at the data, then it says that only 45% of the CO2 that has been emitted in last few hundred years has accumulated in the atmosphere. The rest 55% is getting removed by the ocean and the land. In the land, we all know that we have plants who can do photosynthesis, and photosynthesis is nothing but a process by which the CO2, atmospheric CO2, is converted into organic carbon, and this is the primary source of food for the human being or the animal on the land. But how ocean removes CO2? I hope you are aware of it to some extent, that there are two primary ways by which the ocean removes atmosphere. One is called the solubility pump, where the colder water can hold more gas or can absorb more gas, and then when this colder water is transported to the deep, particularly at the polar oceans where the deep water formation takes place, the more dissolved carbon dioxide in the water is getting transported to the deep. And since the ocean mixing time is roughly 1,000 years, so once the water sinks, the atmospheric carbon dioxide which is dissolved in the water and which goes to the deep is removed for at least 1,000 years. But this is only the half part of the story. The second half part of the story is that we have something called microplankton or the phytoplankton, which we say, which are in function similar to what they do in the plant. They can also do photosynthesis in the presence of the sunlight, and they can also contribute to the removal of the carbon dioxide. And it is one of the major pathways by which the carbon dioxide is removed. But just to throw you some numbers, if you look at the biomass, which is the amount of the chlorophyll or the pigments that are available on the land, is almost 100 times more than what we see in the land, what we see in the ocean. But ocean is equally effective in removing carbon dioxide through this process. So what happens in this ocean? In ocean we have something called photic zone. This is the zone where the sunlight can penetrate. Please remember that the ocean is very vast and very deep. The depth maximum goes up to say 11 kilometers, but mostly the sunlight can penetrate only into the upper layer, few hundred meters, or to be very precise, it is top 100 meter at the most where the sunlight can penetrate. So all these phytoplankton which can do photosynthesis, this process is limited to the zone where the sunlight is present. So when the sunlight is there, the microplankton or the phytoplankton can do photosynthesis as done by the plant on the land. They can convert this inorganic carbon dioxide in the presence of sunlight, make it organic carbon, which is then available for the other trophic levels, for example zooplankton, fishes, small fishes, large fish. In fact, all the biota which is present in the deep ocean is sustained on the primary productivity in the upper ocean, or the photosynthesis process in the upper ocean. So before going into much detail, let us now concentrate first on the zone where the light is playing a major role. The light can penetrate, as I said, mostly up to 100 meter depth, and the water is very clean, and if you reach to the coastal level, then it is further low, few meters only. So light decays exponentially in the upper water column as per the equation Iz is equal to I naught e to the power minus kz, where Iz is the intensity of light at a particular given depth z. I naught is the intensity of light at the surface. We can assume that it is 100, and then this kz, where the z is the depth and k is called the diffused attenuation coefficient. So depending upon the property of the water, property of the substance that is dissolved in the water, the k varies from region to region. In the coastal region it is very high, in the open ocean it is very low. So this is how the light varies in the upper ocean, or with the definition of the photic zone, and whatever process takes place is limited to the photic zone only. Now before we go into the greater detail, it's not that light will always increase the productivity. People have done experiment in the varying condition of light and found that at the low light level the productivity is linearly proportional. As you increase the light, the productivity increases, but if you keep on increasing the light, at some point of time the productivity saturates. Since every sample will have different biomass, the best way to look it as is take amount of sample and normalize it with respect to the biomass, which is your, for example, y-axis is the primary production normalized to the biomass, and if you plot these things on the graph, then the empirical relation shows that the initial slope is defined as alpha b, and the maximum productivity is defined as the PMB. Basically it is productivity maximum normalized to biomass, and alpha is the initial slope normalized to biomass. And these two parameters are important and called PI parameters, which are used to estimate primary productivity on a large scale. If you want to estimate the productivity using some other means, for example the satellite derived chlorophyll values, then you will need these two parameters to do, and these are done only through experiments in in the natural condition. So before we proceed to the other things, let us first define what is primary productivity. Primary productivity is the rate of the conversion of inorganic carbon dioxide into the carbon dioxide. Now please remember that when the phytoplankton do this photosynthesis, they also consume some part of this for their own survival or for their own energy needs. So the total amount of carbon dioxide that the phytoplankton are able to assimilate is called gross primary production, and whatever is consumed for their own survival and own respiration, if you subtract this, the respiration component from the gross primary production, that is called net primary production. So most of the time what we measure is the net primary production. As I was saying that there are two methods by which carbon dioxide can be removed. One I explained as the solubility pump, where the carbon dioxide is removed depending upon the solubility of gas in the water. Colder the water, high solubility of the gas, and when this cold water at the polar region sinks, they carry a lot of carbon dioxide along with them to form the deep water, and the CO2 is removed from the atmosphere. This is the another way, which is called the biological pump, where biology plays a role. In the upper layer photic zone, the phytoplankton do the photosynthesis, they produce the organic carbon, and as they die or they try to settle down, some component of that primary production is getting transported to the deep, and this is one effective way by which the carbon dioxide is removed from the atmosphere. Now some part of this organic matter which is getting transported to the deep is also getting recycled. They are decomposed in the deeper layer. The other organism depend upon these as a source of their food, and for each layer the efficiency of the pump decreases. But in a nutshell, this plays a major role to remove the carbon dioxide. Now the study starts here. We say that the primary productivity takes place in the upper zone, which is called photic zone or euphotic zone. But this zone, despite having everything, is not very high productive at all the basins. The factors that hampers the productivity or that can stop the productivity is called limiting factor. And one of the most limiting factor in the upper ocean is the availability of some key elements. They are called nutrients. These nutrients act like a fertilizer we use on the land, and these nutrients are not present in the ample concentration in the upper zone, and very often they limit the productivity. So if you look at the most common nutrient, which is the N-based or the nitrogen-based nutrients, they limit the productivity in the photic zone, but their concentration is more in the deeper layer, also called as photic zone. And we will try to understand in this talk why the concentration is low in the up and the high in the deeper waters. So if you look at this depth-wise distribution, this we have already seen that the light decreases exponentially as we go deep into the ocean. The photosynthesis is high in the upper layer and the low in the deeper layer. And why it is low is because of the nutrients. The yellow curve shows the distribution of the nutrient in the water column. You can see that in the upper water column, very close to the surface, the concentration of the availability of the nutrient is very low, and because of this low availability, the productivity is not that great. But as you go deep, where the light is very less, the concentration of nutrient also increases primarily because of the decomposition of what is being produced in the surface layer. And sometimes when the concentration is optimum, where the light is also there, the biomass is there, and the nutrients are there, sometimes you get the deep chlorophyll maximum. If you plot chlorophyll on the top of it, then you will see a little hump where the light level is low but the nutrient level is high. So in the upper layer, the light is there, the nutrient is not there, primary productivity is low. In the deeper layer, nutrient is there but the light is not there, so the productivity is low. And there is an optimum depth where both are present in the optimum condition, and we find that the deep chlorophyll maxima is most often present at that particular depth. So in this plot, what I'm trying to show you is the profiles of few key parameters. For example, temperature. We all know that as we go deep, the temperature decreases. Also the oxygen. The oxygen, since the upper layer is in contact with the atmosphere, and also the phytoplankton produce oxygen. So the upper layer is most often always saturated with the oxygen. But as we go deep, where the upper layer stops interacting because of the strong thermocline, the upper layer stops interacting with the upper layer or the atmosphere, and the consumption of the oxygen increases for the decomposition or for the survival of the other oceanic biota. The concentration of the oxygen decreases as we go deep. Much deeper if you go, then there are chances that the oxygen concentration increases. And most important contribution for this increased oxygen at a much deeper level is the same water which was sinking at the coast, at the polar ocean, taking high amount of CO2. Since it is cold water, the concentration of oxygen is very high, and they often act as a source of oxygen for the deeper water. Coming to the right panel, where I am showing the two major nutrients, nitrate and silicate, you can clearly see that the upper layer, few meters, the nitrate concentration is very low, so is the silicate concentration. And as we go to the deep, because of the decomposition of the organic matter, the components are again liberated into the water, and the concentration of nitrate increases, concentration of silicate also increases. These are just to show the two examples of the nutrient. This is true with most of the nutrients. So how this nitrate is distributed in the world ocean? In this figure, we are seeing that major part of the ocean, in fact, if I can say 80% of the ocean is productivity is limited because of the unavailability of the nitrogen. You can see all this blue part where the concentration of nitrate is very low. But there are regions in the polar region near the Antarctica coast, you can see, and also near the Arctic coast, where the concentration of nitrogen or the nutrient is very high. But in that region also productivity is low. If I can take 2 minutes to explain why the situation is like this in the polar ocean, there are primarily for two to three reasons. First is that the light at the polar ocean is very low. So though the concentration is high, the light intensity is not sufficient to convert this into the productivity. Second important factor is the mixed layer. Mixed layer is too deep in the polar regions. So even though some light is there, the phytoplankton, because of the deep mixed layer and the shallow fatigue depth, the phytoplankton do not get enough time in the sunlit layer to produce. And since the mixed layer is deep and the deeper water has more of the nutrients, they are brought into the surface, and one reason for the high nutrient concentration in those regions. The third factor, which is often people advocate, is the presence of the high zooplankton. Since the phytoplankton productivity is not that great, and the zooplankton demand for the demand for the primary producer for the survival of the zooplankton is so high that they are often consumed by this zooplankton, and they do not get enough time to be in that layer to produce. So these are some of the factors which leads to the sustenance of high nutrient in these waters. Late 80s or late 80s, 89 or 90, I would say, the Professor Martin proposed a hypothesis that the productivity in this zone, despite having high nutrient, is low because of the unavailability of another nutrient which is iron based, and since they are required for the enzymatic purpose, and since this iron is not there in the water in the sufficient amount, the phytoplankton are not able to convert them into the productivity. And he proposed a famous theory that if we add iron into these parts of the basin, then the productivity will increase, and we may soon end up in a ices. So he gave a one liner that give me half a tanker of iron and I will give you an ices. Later many experiments were conducted in these basins, so-called the HNLC region, high nutrient low chlorophyll regions, to test the iron hypothesis, and it was felt that the addition of iron sometimes do increase the productivity, but it will not be enough to bring us an ICS. These are some of the major nutrients that phytoplankton need for the primary productivity, which are some of them are the hydrogen based, nitrate, ammonium and urea, and then there is phosphorus based. Then of course we have silica, because many organisms are, their festules are made up of silica. For example, atoms, if the water is devoid of silicate, then they may not be able to grow, because they need silicate to convert their skull. And it was observed that in roughly the concentration of carbon to silicate to nitrate to phosphate is fixed in the water column, which is 106:15:16:1, and this ratio is called the Redfield ratio. Now there are instances where this Redfield ratio does not hold true. For example, there is a process called nitrogen fixation. In the nitrogen fixation, there are certain class of phytoplankton which can take directly the atmospheric N2, dissolve in the water and convert them into for their own use. So in such a case, this stoichiometric ratio is not maintained. Then we have this process called denitrification, which is most prevalent in the oxygen S condition. In this denitrification, the ocean tends to lose hydrogen. I will explain in later slides how it happens. So in the case of denitrification, again the N will be lost, but the phosphorus will be conserved. So the ratio of N is to P will be different than what we see in the Redfield ratio. Just to summarize what I said earlier, that the data shows that the C is to N is to P. The ratio is more or less fixed in the ocean, 106:16:1, barring some few instances where there people have observed this discrepancy, but more or less we can assume that this ratio is fixed. And this is mainly, and based on this, people have tried to give an equation for the photosynthesis, which is listed below. But the major part we have to understand here is that the carbon dioxide is consumed by the photosynthesis, and photosynthesis plays a major role in the removal of carbon dioxide from the atmosphere by the means of photosynthesis. But that photosynthesis to take place, we need some amount of nitrogen, some amount of phosphorus, and the end product is the oxygen and the organic compound. This organic compound or organic matter is the source of food for all the other biota who are not able to produce for themselves, and this is the only source of oxygen, and this is how the oxygen came into the atmosphere for the first time in the history of the earth. So just a few minutes back I tried to explain that in what circumstances this N is to P ratio will be changing. One is the hydrogen fixation, where the source is N and this process is independent of P, so we will get more N, so the N by P ratio will be increased, N will be more and P will be less. But on the other hand, when we have this denitrification and the NMOX, which also takes place in the unavailability of the oxygen, where we lose the N but P is conserved, so again N by P ratio will be different than what we see in the Redfield ratio. Now where this N comes from for the primary production to takes place? There may be various sources. If you are close to the coast, one of the major source of N is the river or the lakes. We use these fertilizers for the agriculture on land, and these are washed away and brought to the sea. At the present time, this is one of the major source of N to the coastal waters, and we often talk about eutrophication, which is basically the transport of so much N into the water that productivity increases tremendously, and to consume that or to degrade that productivity, the oxygen is consumed and the water becomes anoxic, where no organism can survive, and this is called basically the eutrophication. The nitrogen also comes from the atmospheric deposition, but that quantity is very small. You all have studied in your school days that the lightning in the sky often leads to the fixation of the N. By fixation of the N, we mean that the gaseous form of nitrogen is made available for the biotic use in some fixed form. But once we come to the open ocean, one of the major source of nitrate to the upper ocean is through deep. You remember that all these phytoplankton which are getting produced or which are making this primary production in the upper layer, at some point of time they die and they are transported to the deep. When we falls or when they fall below the thermocline or a certain depth, they start getting decomposing. And in this process of decomposition, all these basic components which are used for the primary production are disintegrated into their parent form. And this is the one reason why we have more of nitrogen or more of nitrate in the deeper layer. If for some reason this deeper water comes to the surface, for example through upwelling or through mixing, the deeper water comes to the surface, then they among with themselves, they also bring this nutrient into the photic depth, and they are the major source of primary production. So based on the source of this nitrate, we can divide the primary production into two: the new production and the regenerated production. New production is that component of primary production which is supported or which is fueled by the nitrate which is coming from some other system, for example the deeper water. And the regenerated nutrient is some part of this organic matter is getting recycled or regenerated in the same photic depth, and when they are recycled, they also liberate the nitrogen in the form of ammonium and urea. So those component of nitrogen or production which are fueled by the ammonium and urea are called the regenerated production, and the sum of these is called the total production. The one usefulness of this new definition is that you can define a parameter called F ratio, which is a ratio of the new production by total production. And if you have the estimate of primary production, for example using PI parameters and the satellite derived maps of primary productivity and the F ratio from the measurements, then you can directly try to estimate the export production. Because for the system to continue, whatever is coming to the top has to be balanced by whatever goes down. If we only keep on pushing things to the top and nothing will go down, then at a point will come when the concentration of nutrient in the deeper layer will start decreasing, and in future there may be a scenario when we don't have any nitrate in the deeper layer which can fuel this new production. On the other hand, if we stop putting things, or if you recycle everything into the photic zone, then also in future there will be a demand for the nitrate which will not be able to make. So to balance this system, it is important that the transport of nutrient from the up or from the deeper layer to the upper layer is getting balanced over a longer time scale by the export production. So this new production gives an indirect estimate of the export production. So what happens in the deep? These organic matters, in the presence of the oxygen, they are decomposed to their normal form and they liberate the carbon dioxide and the nutrients. This is one reason why the nutrient concentration in the deeper water or the CO2 concentration in the deeper water is high. This is important also for the sustenance of the system. If the export stops, then the deeper water we will not get anything, and we will not have any nutrient which can be brought to the upper layer through upwelling or mixing in future if we don't export anything now. So what happens to the oxygen? Oxygen is a byproduct of photosynthesis, and it is consumed by the biota in the deep, both for their own respiration and also for the degradation of this organic matter which is getting exported to the deep. And this often leads to the formation of a zone called as oxygen minimum zone, where the concentration of oxygen is very low in this layer because they are not in direct contact with the atmosphere. They are separated from the upper layer, and the oxygen demand for the consumption is high in that layer because of respiration of the other community as well as for the decomposition of the organic matter. If you look at the oxygen concentration or oxygen distribution over the world, then there are zones where this oxygen minimum zone is quite prominent, and for example in the Peru-Chile coast or in the Pacific, North Pacific and South Pacific, and one of the biggest oxygen minimum zone in the Indian Ocean, where the Arabian Sea and the Bay of Bengal both are, the subsurface layer has low oxygen. When I say low oxygen, then this is the typical case. What happens if you try to profile the oxygen concentration? The upper layer has oxygen and it decreases very sharply below the mixed layer or below the thermocline, and then you go to the deep, the oxygen concentration is very low. Very deep, yes, the oxygen concentration increases slightly, mostly because of the input from the polar ocean. The deep water circulation often gives a little bit of oxygen in the deeper waters. Coming back to the Arabian Sea and the Bay of Bengal, both are very strong oxygen minimum zones, but the difference is that the Arabian Sea oxygen minimum zone is bit deeper compared to the Bay of Bengal. In the Bay of Bengal, the freshening of the bay because of the transport of fresh water from the river limits the interaction between the upper layer and the deeper layer, and the upper layer is very shallow because of very strong stratification. And also if you go to the deep, there is slight difference between the oxygen concentration in the Arabian Sea and the Bay of Bengal. For this reason, the Arabian Sea is almost close to the zero level, called anoxic level, where the process of denitrification, I will show in the next slide, it happens. But in the Bay of Bengal, there is a bit of oxygen, a bit more than what we have in the Arabian Sea, and it makes a huge difference in the terms of that the denitrification is not observed in the Bay of Bengal, but it is observed in the Arabian Sea. But the recent data using some high quality measurements or high quality sensors indicate that the Arabian Sea may be also on the verge of denitrification. So to summarize, in the Indian Ocean, OMGs are found in both Arabian Sea and the Bay of Bengal. Arabian Sea is the most intense, and depending upon the oxygen concentration in the deeper layer, we can define the zones into oxic zones, hypoxic zone, suboxic zone, and anoxic zone. Anoxic zone is where the oxygen is very close to zero. Suboxic zone where the oxygen ranges between 2 to 10 micromole per kg, and hypoxic zone is the oxygen concentration is below 60 but more than 10. But the oxic zone is the upper layer where the oxygen concentration is quite high. So what is this denitrification? As the oxygen concentration in the deeper layer goes down, the organism starts looking for other source of oxygen, and the other major source of oxygen in the deeper layer is the concentration of nitrate, which has 1 N and 3 oxygen. So these organisms start taking oxygen from the nitrate, and then NO3 becomes NO2, NO2 becomes NO, and subsequently it goes to N2 gas. So this pathway by which the bioavailable NO3 is getting converted to the inert, I would say, N2, this process is called the denitrification. Now denitrification is the one pathway. Another pathway is which is discovered say 10-15 years back is called NMOX, where the 1 mole of ammonium which is coming from the degradation of the organic matter and 1 mole of NO2 combines together to give N2. So all these intermediate things are escaped in this process. There is another method also called DNRA, but I will not go into the detail. What is the take home in this is that because of this denitrification, ocean is losing the bioavailable nitrogen, this is believed to limit the productivity in the surface layer. So as we go into the era where the expansion of the oxygen minimum zone or the deoxygenation of the ocean takes place, this will strengthen the denitrification process, which will enhance the loss of N2 or loss of bioavailable nitrogen from the ocean system, and which will further limit the productivity. So it has a larger consequence in terms of the carbon removal from the atmosphere by the ocean as is concerned. This is just to show, which I have explained already earlier. This is the plot of the ratio of nitrogen to phosphorus, whatever data has been collected up to date. And you can see directly that the N2 fixation is not very common, but the ratio of N is to P, for example, upper half of the graph shows the nitrogen fixation where the N is more, and the lower half shows the denitrification where the N is removed and the phosphorus is increased, and hence the ratio is increased. So this plot summarizes that the major chunk of the ocean is prone to denitrification. For example, we saw that Arabian Sea and the Bay of Bengal and the Pacific region. Nowadays, because of this eutrophication, the coastal waters are also getting anoxic, and there also this denitrification process may be taking place. So this way we are already losing, and if the expansion of the oxygen minima continues because of this global warming, then further this ocean will lose nitrogen. There are already reports that, as I said earlier, Bay of Bengal high quality measurements show that Bay of Bengal is very close to being a denitrifying zone, and the model based study already are indicating that ocean is losing oxygen, the deoxygenation of the ocean is taking place, and as per the one of the estimates that the oxygen will decrease by more than 7% by 2100, and coastal sites are more prone to this because of the eutrophication, and there are likely chances that 500 more such sites will be generated. The end point of this deoxygenation is that the fisheries will 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 tend towards collapsing if we keep on losing the oxygen from the ocean, because they cannot survive in the low oxygen concentration. Now, how it is going to affect in terms of the global warming, then I have tried to summarize what will happen if we increase the temperature. For example, global warming will lead to the surface heating. Surface heating will lead to increased stratification. This increased stratification will change the oxygen in two ways. One is that it will lead to less upwelling, because the water will be more stratified. The deeper water will not be able to reach to the surface, so upwelling will be reduced, or the mixing will be reduced. So the transport of nutrient will be reduced, the production will be reduced, and hence the export production will be reduced. This will lead, the decrease in the export production will lead to less oxygen demand, and some increase in oxygen we may feel in this pathway at the deeper layer. But if the opposite way of this is, if the ventilation is low, then the supply of oxygen from the atmosphere to the water will also be reduced. The net availability of the water, net availability of the oxygen will be compromised, and the ultimate effect will be that the oxygen quantum of oxygen in the deeper water will ultimately decrease. So it has many facets of this. The global warming will affect in many ways, but the end product will remain the same, that the oxygen inventory of the deeper or the surface layer will decrease. Thank you. If you have any question, I will be happy to answer. Only one question. So I have got one question, like what would be the likely effect of dumping of tons of plastic produce into the sea and the ocean? What is the present effect of garbage jars of the Pacific Ocean on these components? There are many things which dumping of plastic can do to the ocean. If you fill the surface layer with the plastic, you are going to cut off the exchange of the upper layer and the atmosphere, and it will have an impact on the exchange of the gases, for example the oxygen. It will also play a major role in cutting off the sunlight into the water column, and it will ultimately affect the productivity. These were the aspects of the biogeochemistry. But the plastic itself is very harmful. You must have seen millions of pictures of this organism getting entangled into the plastics. So it is very hazardous for the marine biota in any form. Any more questions? Okay, I am told that you will get 5 minutes for asking questions, so I will be on a standby. The second question is what would be the likely effect of dumping of various chemical products by the industries into the tons of liters into the sea or the ocean? It will the hazardous chemical are going to have a very bad effect on the coastal ecosystem. It can decrease the pH, and then it will hamper the those organisms or the fishes. For example, corals, whose skull is made up of calcium carbonate, and they cannot sustain a lower pH condition. So all those will start dying. And you all know that the corals are very rich zones of biodiversity. So once we start killing the corals by dumping the chemicals into the sea, the whole ecosystem will collapse in that region. So ultimately, it will affect the the biota, the ecosystem in that zone where it is dumped. And in my talk, I also touched upon the effects of the eutrophication, like the amount of fertilizers that we use, and they are getting washed away to the coastal seas. They will this enhanced flux of nutrients into the coastal sea will artificially increase the productivity, and this increased productivity will lead to the decline in oxygen at the deeper layer. They will occupy the surface, and they will cut the interaction of the layer to the atmosphere and the exchange of the gas. They will they will act as a barrier to the atmospheric exchange. The oxygen concentration will go down. The zone may become anoxic, and there are we often define them as a dead zone, and there are already evidences that the number of dead zones in the world ocean has increased dramatically in last 20-30 years. So all these will have effect. The another question is, how are the factors irradiance and denitrification is related? The irradiance will affect the productivity, and the denitrification will hamper the, or it will affect the quantity of bioavailable nitrogen present in the system. If you look at the coastal waters, the the number of particles that the coastal water has, for example sand, the organic matter, debris, all these lead to a very shallow fatigue depth, and this very shallow fatigue depth will limit the productivity in that particular depth itself. In a case where these coastal water are additionally getting dumped by this fertilizer based nutrients, fatigue depth is low, the nutrient will increase from the coastal supply or the estuarine supply, the productivity will increase in that low fatigue depth area itself, and the productivity often increases so much that it kind of forms a layer in the upper zone, and it stops the exchange of that particular layer with the atmosphere. So the supply of oxygen will decrease. At the same time, since the productivity is very high, the demand for the oxygen will increase in the deeper layer. So the supply is reduced, the demand is increased, so the zone will become highly anoxic or close to anoxic, and the ecosystem at that place will die, and we define such zone as dead zones. In the open ocean, however, the irradiance is limited to the upper 100 meter, which is well illuminated, well ventilated zone, but the denitrification takes place below this mixed layer or below the thermocline depth. So any change in the productivity for some reason in the upper layer will lead to the change in the export production to the deep or the subsurface layer, and it will again change the demand for the oxygen in that particular subsurface layer. I think there are no more questions, so I will stop here. You can always send me your queries in the email satyap@incoas.gov.in, and I will try to answer to my best capabilities. Thank you for your time, and thank you for listening to my talk.